Okay, in this experiment, we're gonna investigate if one important thing with this a slotted waveguide antenna. So if you remember, from one side of it we have our excitation, from the other side we have our short circuit, so the metallic plate. Now, if you remember, I was explaining that the distance from the metallic plate to the center of the last slot here should be quarter wavelengths plus multiples of half a wavelength. So, and that's exactly that for this purpose. So this distance that we have the metallic plate to the center of the slot is about 2.73. Whereas if from this side, from the edge of the waveguide to the center of this slot over here, it's about 3.64 centimeter. So 3.64, and then this is now 2.73. 2.73 is the correct one to have the metallic plate, the short circuit here. Now, we want to investigate what's going to happen if we don't do that correctly. So I'm going to now move, this is the excitation. I'm going to put the excitation here, and I'm going to put the metallic plate here. Now, the metallic plate is going to be here, and it's going to be separated from the last slot over here by about 3.64, which is not a quarter wavelength plus multiple of half a wavelength. Now, we want to investigate the degradation in the radiation pattern of this antenna. So let's do that. And so I'm just going to change these two, and I'm going to perform again E-plane cut and H-plane cut. Okay, we have now put the metallic plate short circuit on the wrong side. So the side that the distance from the center of the slot to the metallic plate is 3.64 centimeter. That's denoted by D prime in the student manual. And we also put of course, we put the excitation at the wrong side, which is the excitation would be at the side denoted by D in the student manual. That is 2.73 centimeter. Now, based on these wrong arrangement, we're going to do again our measurement to see what's going to happen. So we want to investigate that it is important that quarter wavelengths plus multiples of half a wavelengths be used for the short circuit. So because now our focus is on right now I've mounted it on the H-plane case. So the only thing that I'm going to keep here, I'm going to hide the E and H plane of the horn antenna, and I'm also going to hide the E plane of the slotted waveguide antenna. So on the plot right now, you only have the H plane under the correct situation. Now I'm going to measure the H plane under the condition that my short circuit metallic plate and the excitations are on the wrong location. So let's do the measurement and see what would be our measurement. So I mean, to have it properly set, we need to wait and it until it finishes, and then we rotate it such that the maximum signal level at 0 degrees. If you remember, we set the maximum signal level to be at 0 degrees. But one thing you can immediately see here is that because now I don't have that metallic plate, that short circuit at the right location, and also the excitation, of course, at the right location, what I'm gonna get would be like a much smaller signal level. That's an indication that this has not been done properly. So I'm just gonna save that under a new document under H plane. So I have it under H plane and under a new document. And what you can see in this case is that the maximum signal level is now smaller. So in this case, I have about 11 dB smaller compared to the previous case. So so this is now my uh, H plane when I didn't use it properly. So it is about minus 14 dB, and the one that I correctly use is about minus 3. So I have 11 dB signal loss because of this mistake in the arrangement of the antenna. So now it's also good to go and do the E-plane and see what would be the situation for the E-plane. So let's go and do the E-plane. Okay, so we are going to continue with our measurement under the situation that the metallic plate and the excitation has been placed on the wrong side. What you see here, that was the H-plane under the wrong arrangement, and this was the H-plane under the correct arrangement. So you see the signal drop when we go to the wrong arrangement. This was for the H-plane. Now we need to go to E-plane. So to do that, let me keep the H-plane under the wrong situation, but I'm gonna hide the E-plane, the H-plane under the correct situation. So this H-plane under the correct situation is gone, and I'm now, the only thing I have is the H-plane under the wrong situation. So now I mounted the antenna under the E-plane situation. So I just rotated the antenna under test 90-degree. Something I forgot to do that, and I just remembered that, is that when I rotated the antenna under test 90-degree, I also need to rotate the transmitting antenna by 90 degrees so that I have the same polarization. So let me do that quickly. Okay, I just rotated the polarization of the transmitting antenna so that I have polarization match. So what I'm gonna measure right now would be the E-plane pattern under the wrong arrangement. So let me start my acquisition. So this is the acquisition to see, and as expected from the previous case, our E-plane is broader compared to H-plane, even in the wrong arrangement. So I asked you earlier to justify that, why our H-plane is more focused, is more directive compared to E-plane. So now that our E-plane is finishing, let me wait until it's completely finished, and then we can compare it with the E-plane under the correct situation. So okay, it is now done. So I'm gonna store that under E-plane. Something that I should have done also for the H-plane under the wrong situation was to rotate it so that the maximum signal level at 0. So I'll do that for the E-plane too, to put that under 0. So one thing that you can immediately notice here is that now I have a little bit of gap between the maximum of E-plane and H-plane. Ideally, they need to be identical, but because the signal is now weaker, it's probably more difficult to get the same level of accuracy. So now this is so the maximum signal level for E-plane is minus 13.3, for the H-plane is minus 14.23. Now let me bring the E-plane of the correct arrangement. So this was the E-plane of the correct arrangement. So you see, if I just keep the E-plane on the wrong arrangement, so now you're comparing the E-plane under the wrong situation with the E-plane under the correct one. So the overall, the pattern is almost identical. It's just the signal drop because of the wrong arrangement. Now I could bring the H-plane too. That's under the correct case, and this is the H-plane under under the situation that we have mistakenly used the short and excitation. So just one more, just comparing the H-plane under correct and the wrong arrangement. Now we go to E-plane, and I'm gonna hide the H-plane. So this is the situation that we have, and in both cases we have about 11 maybe 10 dB signal drop when we have it in the wrong arrangement. Okay, what we're gonna do in this lab is to investigate what's gonna be the effect if we decrease the number of elements. So what you see here is that a slotted waveguide antenna that we had, but as you, if you look at it closely, I put two adhesive copper tapes on the two elements on the left and one on the element on the right. So if you look at this closely, I essentially have three elements. What I had from before, I had six elements. So now this is essentially three element antenna array. So we're gonna go and investigate what's gonna be the H-plane cut of this three element antenna array compared to this original six element antenna array. So since this is mounted in the H-plane, and so we're going to be considering H-plane cut. It's also good to mention that in our previous measurements, we changed the location of the short circuit and excitation to investigate bad arrangement, but now it is now correctly placed, so everything is correct. The only thing here is that I have three elements instead of six elements. So let's go and do our measurement. We have now three copper tapes to cover the three slots over this slotted waveguide antenna. It is in H-plane mode. So what we're gonna do, we're gonna run the experiment to get the H-plane cut when the three slots are covered. So essentially we've switched from a six antenna element to three antenna elements. So let's check what would be the radiation pattern. So I'm going to start the data acquisition. So let's start it. The horn is vertically polarized because remember the slots are also vertically polarized. So if I can a little bit zoom in so that you can see better. So now this is the back radiation. So it gets closer to, so now you can see the three copper tapes that we have. Okay, so now the measurement is done and we can go check the data acquisition. Okay, what we have right now is the H-plane of six antenna element. So we had six slots over the waveguide antenna. Uh, Let me bring the E-plane as well. You see that the E-plane has a half power beamwidth of 66.32 degrees, H-plane 12.97 degrees, maximum signal level. Although theoretically they need to be identical, due to uncertainty in the measurement, they're slightly different here. One of them is minus 3.31. The other one, which is H-plane, is minus 3.07. So I'm going to hide E-plane. And now I have the slotted waveguide antenna with three slots covered in copper tape. So essentially I have now three antenna elements. So let's perform our data acquisition to see what would be the pattern that we get. So remember, what we want to study here is that if I go from six element antenna array to three element antenna array, what would be the change in the maximum signal level? And I mean, would I expect that or not? So what I want to also mention here that these two patterns have been collected at different times. So I mean, the absorbers locations and things like that are not exactly identical. But here our main focus is really the maximum signal level that we get. So if I store this now, then I can carry on. Okay, let's store it. And let's now compare the maximum signal level that I have for these two patterns. So you see, this was the 6 antenna element with the H-plane MSL of minus 3.07 dB. This was my 3 antenna element, and maximum signal level dropped to minus 7.01. So I have a drop from minus 3.07 to minus 7.01. So I want you to discuss what would what was the number that you expected, and why, and then discuss any uncertainty, any measurement uh, errors that we have here. So that would be the main purpose of these two experiments. Okay, we're gonna go now to our next measurement. So you see what changed between this measurement and the previous measurement was that I added one more copper tape to cover another slot in this slotted waveguide antenna. So essentially in the previous case, I had 3 slots, now I have only 2. So now we're gonna go do another measurement with these 2 element antenna array. Okay, in the next experiment, we're gonna go to another scenario, and in this scenario now we've covered another slot here. So now we only have 2 elements in the array, and now we're gonna do another data acquisition. So let's start our data acquisition and see if it makes sense or not. So from the very beginning, you can see that it had a drop compared to the other 2 measurements. So to just explain that again, the measurement that has the highest maximum is when we had 6 elements in the array. The next one, which the mouse is now pointing, is the one with 6 elements. And then the one that we are measuring that has maximum around here at the mouse, it is when the case that we have 2 elements. Okay, now this is also done. I can go and save it. Okay, so one thing that, so let's start one by one. This was 6 antenna element. The maximum signal level was minus 3.07. This was 3 antenna element. The signal level was minus 7.01. This was with 2 elements. The maximum signal level is minus 9.57. So that's the value that we got. And also you can see on the screen that half power beamwidth changed too. For the 6 element, the half power beamwidth was 12.97 degrees. Then for 3 elements, we are at 28.36 degrees. And then for the 2 elements, we are at 39.79 degrees. Now my question for you is that what you expect from the theory and how close these numbers are to the theory. So you need to explain this. Okay, in the last part of this experiment, we now still have 2 elements, but if you compare it with the previous case, these 2 elements are separated farther. So essentially, the elements that we put copper tape on are now closer. So the 2 remaining elements are separated farther compared to the previous cases. So what I'd like you to do is when we collect the radiation pattern for this new configuration, you justify it based on the increased distance between these 2 elements. So that would be the purpose of this experiment. Okay, so to summarize what we have so far, we have 6 elements, then 3-element antenna array, then 2-element antenna array. But these elements are all separate, the separations are all very close. Now, this new case that we have is a 2-element antenna array, but the elements are spaced farther from each other compared to previous cases. So we want to investigate what's going to happen under this situation. So let's start our data acquisition. Okay, it's finished. Now I'm gonna save that. Still, I'm using H-plane. So, okay, now I have my pattern. I can move it to a maximum signal level to 0. And now, if you look at this, the question is why we have this scenario, and can you justify it based on the theory? So that's essentially my question for you. And so let's see if we can answer this question. Okay, now let's go back to the plot that we have. Right now we have our 6-element antenna array over here. And this 6-element antenna array, remember that the frequency of operation is 10.52, and the separation between two successive elements is 1.82 centimeter. So 1.82 centimeter would be the separation between two successive elements. And so in that case, this would be our pattern, which is very directive. Then we decrease the number of elements in the next example to 3. So in this case, we were dealing with 3 elements. But the key thing here was that in this example, still the separation between successive elements were still 1.82 centimeter. So in the next example, we made the number of elements 2, but still the separation was 1.82 centimeter. Now, when we went to this last example that we have over here, this example, the separation between the two elements, it was only 2 elements in this case, but if you remember, the 2 elements were farther from each other. The separation between these 2 elements was 9.1 centimeter. So remember that we went from, in this case, 2 elements with the separation of 1.82 centimeter. We increased it 5 times, so we now end up to be 9.1 centimeter separation in this case. And now, based on the array theory, you know that if you go beyond a certain distance, you start having grating lobes, and this is the effect that we have over here. Now, one thing because you need to justify why we have these lobes, and I want to make sure that you understand one thing here. If you look at the formula that we have in our lectures, it is assumed that the direction of maximum radiation is 90 degrees. So in this case, the way that we arrange that, the direction of maximum radiation is at 0 degrees. So just to be consistent, we could perhaps rotate it to be at 90-degree, because this is a broadside array. It's perpendicular to the axis of the array. So maybe what I do, I'm gonna hide all of these other pattern, and I'm just gonna keep that. And when I'm keeping that, maybe I'll rotate it so that the direction of maximum radiation is at 90-degree. This way, I'm going to be consistent with the textbook, and I'm going to be also consistent with my own lecture notes. Now, I have two cursor here, so I'm just going to place one of them right at 90-degree, and I'm going to move the other one. So now that I'm going to move it to this to here, you could see from here that this angle is the difference between this 90-degree and this angle is essentially 17 degrees, or 70, and the angle itself is 73 degrees. You could see it here. So this uh, cursor that I have here correspond to angle 73. So you should see if that 73 makes sense or not. And of course we have it on the opposite side too. So we have it here too. And in this case you are looking at again 70-degree separated from the 90-degree, and the angle is 107. So this is a symmetric situation. Let's assume it's symmetric. So here I'm gonna again be here, it's the difference is 17-degree, the angle itself is 73 degrees. And now if I go to the other one, I'm looking at about 38-degree difference from the 90-degree, and the cursor itself is at 52 degrees. So would that make sense based on the array theory that you have? And now I could move it to here too, and in this case the difference is 62 degrees from the 90-degree, and the cursor itself is at 28 degrees. So now based on the frequency of operation, which is 10.52 gigahertz, based on the fact that we know that these two slots are in phase, so the phase difference is 0. So in our formulation, beta is essentially 0. The separation is 9.1 centimeter. We want to know if these extra lobes that we have make sense or not. So that would be your responsibility to check and explain these.